Welcome, everybody, to Strange Loop and to the Day of Datomic. My name is Stuart Halloway. I'm a founder and at Cognitect, based out of Durham, North Carolina, which is the company that makes Datomic and Datomic Cloud. And just a few logistical announcements before we get started. If you have questions throughout the day and you're having trouble finding a human face to make eye contact with, you can ask in the Day of Datomic room in the Strange Loop Slack. It appears that about 95% of you are safely ensconced there and able to do that. Those of you who were not able to get in there, we can work on trying to get you in there. The other option is to get into the closure Slack, which is a more public Slack, and ask in the Datomic room there. A third option is to ask Joe Smith, who works with me at Cognitect, currently sitting in the back of the room wearing the Datomic shirt. We have tables for people to sit at. We do not yet have power run across to the tables, so there is power on the sides of the room and in various corners, and when we do our lab breaks, we can sneak away and get to where power is to recharge laptops. We're going to try to be bringing in power during the day so that we can resolve that issue. Does anybody have any other logistical questions about the day that I should speak to before we get started? This will be a forced march. There's no lunch break or other break of any kind. Okay, I was just kidding about that. So lunch will be approximately 12 to 1, I believe, and there will be an extended break in the middle of the afternoon around 2:30, and we will have breaks in addition to that. The format is about half this and half hands-on for you playing with Datomic. So we'll be talking about Datomic and then playing with it. So I'd like to tell a story, sort of the history of databases in 6 words. And the 6 words that I want to use are, I'm just making sure you're seeing what I'm seeing. Okay. The 6 words that I want to use are these: transactional, logical, hierarchical, flexible, indelible, chronological. Once upon a time, software developers needed to put data somewhere and get it back later. And it's worth thinking for a minute why we do that. Would it make sense for me to say that a hard disk is a database, for example? And a hard disk is a place where I can put data. A hard disk is a place where I can get data back later. But most of us would not think of a hard disk as a database. And so there's a set of characteristics, and admittedly, these are contested. People disagree about what the important characteristics are. And the same characteristics do not help for different kinds of problems, right? We've discovered gradually that maybe one size does not fit all with databases. But if we rewind the clock a little bit, once upon a time, there was general agreement about how to put things in databases, and we put things in relational databases using SQL. And there were good, really potent reasons that we did that. One of those reasons is that SQL databases are typically transactional. They have what are called the ACID properties. So when you are putting data into the system, your changes are atomic. So you have a batch of changes that represent, say, taking money out of all of your bank accounts and putting money into my bank account. We want all of those things to happen atomically. Otherwise, we have a problem that we've accidentally created or destroyed money, and you get that like Superman 3 plotline kind of problem going. So you want things to be atomic. You want things to be consistent. There's a lot of different things we could say about consistency, but let me just say right now, we want participants in the system to see the world unfold in a common order. So if I look at the series of events that happen in the world, and you look at a series of events that happen in the world, we both see the same order. So we could say more about consistency, but I'll say that for now. We want our work to be isolated. So when people think of transactions as something that's this ongoing process, they don't want to see other people's in-process work, and we want things to be durable. So once we put data in the database, we can get it back. And even when you just talk about these properties, you understand why storing things in a file doesn't have the ACID properties, right? It has some of them. It's worth thinking through, which ones it does, but it doesn't have all of them. And making a database transactional makes it incredibly easier to reason about your data, right? You always know what you have, and you always have things come in cohesive units, and you can always get back to them. So this is a beautiful thing, and there was much rejoicing. In addition to this, though, you want to get data back out of your database. So if I said, write a for loop, or maybe 6 nested for loops to get data out of a database. Now I'm going to spin through this, and then I'm going to spin through that, and then I'm going to spin through the other thing, and then I'm going to spin through that thing. You probably would not call that database access. Right? That doesn't feel very much like a database. It feels very imperative. It's error-prone. It's very rigid. And so the other thing that SQL databases gave us was logic. Right? You don't do imperative programming or functional programming in a SQL database. You do logic programming, and you don't say how to get the information or too much about where the information is. You just say what you want. And then there's a query engine and optimizations and decades and centuries of human effort in tuning query engines to be able to efficiently say, you know what, we're going to take the burden of how you get the stuff off of developers and put that burden on the database. And so that was also a very, very good thing. Now, because of these two characteristics, SQL databases sort of got a monopoly on how people think about doing data, and that monopoly lasted for a long time. And the monopoly was broken, I would argue, by two ideas. One that's really blindingly obvious as you've watched it unfold, and the other one may be a little more subtle. The first idea was this notion of being web scale. So it turns out that the kinds of mechanisms that traditional relational databases used to give you transactions and logic worked really great when you had millions of things, and maybe worked pretty well when you had billions of things, and maybe worked a little bit less well when you had trillions of things, and maybe were completely right out when you had a quadrillion things. So people were creating data systems that had to have huge write volume, and the phrase we're going to use about that today is write scale. People were building what I'm going to call write scale systems, and they discovered that the traditional SQL databases weren't doing a very good job of that, and so that created an opening into which MongoDB, Cassandra, Riak, DynamoDB, a lot of NoSQL databases that you've heard about, jumped in. And that was great. It doesn't actually matter for most of us, right? There are tons of applications that do not need write scale, but the fact that they sort of broke the logjam on our thinking about databases was great for everybody because it opened a door to solve some other problems with relational databases. So in Datomic, we're not interested in solving the write scale problem. We've explicitly made a trade-off at the very top. We are not interested in write scale. That's not the problem we're trying to solve. There are lots of people out there working on that problem because we felt that there are a number of other problems with relational databases. One of the problems is, what happens when you have to model hierarchical data? So you have this data relates to this data, relates to that data in a loop, and back up to that data. It turns out that tables and joining across tables starts to feel a little bit stretched when you're trying to model hierarchy. And hierarchy is really just the tip of the iceberg of flexibility. There's all sorts of things that start to fall down when you have to predefine a set of rigid slots of information. Right? I'm going to describe a person, in my address book. So I'm going to make some slots: first name and last name and address line 1 and blah, 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 phone number and zip code. And as soon as you commit to those slots, you have future sadness ahead because you're going to discover that your information in the world is not going to match those slots. It's not going to match those slots because you're going to have some additional information about some people that doesn't fit the slots you picked. And other people, you're going to have not enough information to fill in the slots. And is this problem going to get better or worse if you have a lot of slots? It's going to get a lot worse. You're going to have a huge problem. Imagine a system where you have 10,000 different slots of information that could be information about a person. And there are lots of data systems that have this characteristic. One easy one to imagine is an inventory database. Someone who's keeping track of stuff that they have. Well, I'm interested in recording certain facts about the shirts on the shirt aisle, and I'm interested in recording entirely different facts about the glue on the glue aisle. If I'm a department store, and I'm interested in recording entirely different facts, but those things are all in my inventory. So in some contexts, they're all the same. So there's a lot of rigidity that comes from setting down slots in advance. And by the way, this rigidity doubles down if you use object-oriented programming in a very typical fashion, because you're going to do exactly the same thing, right? You're going to say, you know what, I'm going to make a person class, and my person class or address book entry class is going to have in it some slots, and no sooner than you make those slots, what happens? Along comes a piece of information or an entity in the world about which you know more, or along comes an entity about which you know less. Not to mention that they don't compose very well. So let's imagine that I have an address book table and a Twitter account table. Can those things have rows that are talking about the same world entity? Absolutely. Right? I can have a Twitter account and I can be in an address book. And I can have a separate GitHub account. In fact, God only knows how many accounts do we have. My 1Password, I think, has like 5,000 things in it right now. And every one of those represents data about me somewhere that's probably stored in some slots. But logically, if I were looking at that as just data, if I wanted to have all of that data together, I would just say, merge these maps. Right? Take this map and that map and that map. But as soon as we get into slots, we're in trouble. So it turns out that slots are bad for hierarchical or flexible data, and a lot of our data in the world is flexible. There's another problem, and this problem dates back to the 1970s or earlier, when a lot of the thinking was done that informs how we do programming languages and how we do databases. And that thinking was based on the idea that memory is really, really precious, and we have to reuse it all the time. In particular, anytime I learn a new fact about something, I have to forget the old fact that I knew. So if somebody moves, then I lose track of their old address. And of course, as soon as people tried to start building systems on top of this muck, they had to come up with all kinds of elaborate workarounds. So you might have shadow tables in SQL that say, this represents my current state of information, and this represents my old state of information. And by the way, then, when you want to query the current stuff, you have to use a different query than querying the old stuff. Slots again, right? You have slots that say the old stuff looks like this and the new stuff looks like that. At the very least, the old stuff needs a slot that says, how old is it? And so then you have to change the shape of your queries to ask about the past. This is really terrible, and it's just wrong. And in 50 years, databases won't work this way as the typical way of thinking. I used to say in 10 years, databases won't work this way, but I've watched how slow people are to adapt new ideas across my career, so I'll push that out to 50 for today's estimate. So the problem is that when you put stuff in a database, you want to remember it. And the word we're going to use for that is indelible. Right? Once you put something in, it's in there forever. And every single one of you, I would guess, certainly if you followed the instructions for setup, have a personal, indelible, distributed, scalable database on your laptop that you probably use every day, called Git. Right? We store our source code indelibly. Right? Do we want to forget what our source code looked like 6 months ago? Absolutely not. Here's a more subtle question. When we discovered that there was a bug in our program, do we go back in Git and scrub the bug out of history so we can't tell there was a bug in our program? I mean, okay, that's a different talk. If anyone has seen my narcissistic design talk, there are places where you might do that sort of thing. But no, you don't want to forget the past, even if you were wrong in the past. In fact, especially if you were wrong in the past. So it's crazy that our databases don't do what Git already shows us is the right thing to do. So Datomic is indelible in the sense that when you put stuff in, it stays there. When you put new stuff in, that accretes. But the old stuff doesn't go away. It doesn't change. Now, once you have a system that's indelible, you get chronological almost for free. You're not forgetting what happened in the past, so now all you have to do is record when you did stuff as you go. And Datomic is going to give two different notions of chronological. It's going to give relative time, which is just an increasing number. So this happened at time 1000, and this happened at time 1005, and you're going to be able to get that information back from your system. But you're also going to be able to know wall clock time. Right? This happened 3 weeks ago in the middle of the night during the full moon, and this happened by the light of day, and so on. So Datomic is a database that says transactional and logical programming is fantastic. We love that about relational databases. We're not going to take on right scale, and we're going to solve these other problems that relational databases have. So that's one strand of the story today. The other strand of the story is that people are moving to the cloud. And I'm going to talk particularly about Amazon Web Services. But generally, people are moving for a lot of different reasons. They want their systems to remain, well, they don't want to have a capital expense, right? They don't want to run a data center anymore. So a lot of people are moving to the cloud because they were told to. People say, we're not going to run this in-house anymore. And we've also been promised a bunch of benefits about running in the cloud, like high availability, right? You used to build something and run it in your data center, and it was on you to make sure there were extra machines and that those machines would come online when the other machines died. Or even worse, you had to go and open up a machine and change a part inside of it when that part died. And Amazon Web Services offers the promise of high availability by treating your compute power as virtual and ephemeral. It could go away, it could come back. You don't care, you don't have pet machines. It also promises elastic auto-scaling, right? All the plumbing is already in place. All you have to do is write a program and say, let me start running it, and I can ask Amazon Web Services to say, you know what, if this machine gets overwhelmed serving this job, and you can detect that in various ways, then we'll start more machines to do that job. And when you get back to the opposite of overwhelmed, I guess merely whelmed, then you can go back the other way and say, we'll stop these machines. We also want security, and in fact, this is often a reason that people don't go to the cloud today. How many people think your organization is smarter than Amazon Web Services and can lock down things and manage the universe better than Amazon can? We're going to have security breaches. Okay. Big companies are going to screw up. Small companies are going to screw up. Amazon's going to screw up. Everybody screws up. But I think the balance for most organizations, except for the very largest or the very most secretive or sensitive, military, is advantage Amazon in terms of being able to automate security for your system. And then, of course, we got out of the data centers because we wanted usage-based pricing. We wanted to be able to say, we want compute as a utility, like power is. So you pay for what you use. And once this transition to cloud computing is complete, we will think about compute the way we think about power. Right? You don't spend most of your time worrying about mitigations for if you flip the light switch and the power doesn't come on. Now, admittedly, I live in North Carolina, so last week when Florence came through, I did get to spend a little bit of time thinking about that. But by and large, we accept that we're going to get power off of a grid, and the move to the cloud and to AWS and Google Cloud and Azure and other things like it is that we're going to get compute off of a grid, and that most of the time we're going to be happy about that. So this is a beautiful world. And all you have to do to take advantage of this world is take your existing data center software and put it into a zip file and copy it up to AWS and press play, and you're good. You guys got to give me more reaction when I just lie to you like that. No, it's not like that at all. There's a different programming model in the cloud. I like to think of AWS as an operating system, right? As a cloud operating system. And that operating system has a slew of primitives that, for the most part, don't have to deal with things like files or individual machines. And so in order to write programs on AWS, you have to some degree, learn a bunch of new stuff. You don't get to put things on disk. You get to put them on DynamoDB. But wait a minute. Should you put it on DynamoDB? Or maybe you should put it in SimpleDB. Or maybe you should put it in S3. Or maybe you should put it on EFS. Or maybe you should hold it in memory in Lambdas. Who knows, right? There's a million different choices for how to do these things. So it's a bit, again, overwhelming to say I'm going to build an application that's going to run on AWS. So the second big strand in Datomic's history is building Datomic to take a lot of the challenge of running on AWS away from you and let Datomic do that lifting. And the way that works is there is an offering on what's called the AWS Marketplace. And when we started researching the best ways to distribute Datomic to people on the cloud, I didn't even know that the marketplace existed. How many people have never seen the AWS Marketplace before today? Right? Certainly was not something that was the most well-known service. What is the most well-known Amazon service, by the way? S3 probably, or EC2, but would be my guess. Right? But there's a lot more going on there. But those are the ones that are, those are the gateway drugs. Right? The person on the street corner with the jacket saying, got some EC2, some S3 here, and then you do that, and like 6 weeks later, you're neck deep in DynamoDB and everything else. But what the marketplace lets you do is it allows you to run Datomic in your account, but with a ton of automation. So this is quite different from running a service. If you put your data in a service, then you are worried about what's going to happen to that service. Right? Is that service going to be there? Are they going to look at your data? That sort of thing. So there are lots of reasons why people have been reluctant to put their database on AWS. They might do other things on AWS, but they don't put their database on AWS. Or they run a database on AWS in their own account. We are definitely trying to split the difference here and give you a lot of the benefit of a service. So all the pieces fit together, and there's automation, and there's monitoring, but it runs in your account. And it shows up as a line item on your AWS bill. So this is important. 90% of new software projects end up needing to be trialed in a very inexpensive, non-challenging way for developers. And then when they work out, you go back and get approval for what you already did. Right? So in your free time, you go and download something that you think might help your org or you become better as a programmer, and you use that for a while, and then you decide you're happy with it, and you go and start using it. So it was important to us and to users who want to try this that this is not an approval process thing. Right? If you have a budget for $100 a month of AWS, start Datomic Cloud, it's a line item on your bill just like EC2 and S3 and all the other things. And it gives you a programming model that gives you elastic autoscaling, that gives you high availability, that gives you security, that gives you monitoring, that gives you redundant durability, and you don't have to do any of those things. You just get to write your program. So how do you start? Datomic ships in 2 topologies. The first topology is called Solo. I really wanted to call it Chewbacca, but the rest of the team overruled me. It's not that kind of solo. Solo means there's only one compute resource. Why would you want only one compute resource? That's sort of the opposite of the cloud thinking, right? This is not highly available. You want only one compute resource because you're keeping costs as low as possible. So this is for, I'm really concerned about cost. But I want to have the full programming model. So the Solo topology delivers all those ideas I talked about, and admittedly that we haven't fleshed out yet about Datomic. It delivers indelibility. It delivers chronological capability. It delivers ACID transactions in a logic-based query language, all running in a very tiny footprint. It's integrated with AWS security and monitoring. It's triply durable, so when you store things in the database, they are redundantly stored to Dynamo, S3, and EFS, which of course is a little bit crazy because all 3 of those storages are themselves redundant. So it's redundant. And then you can access this using a Bastion server, and this costs about $1 a day if you left it on 24/7 to run. So this is the very small footprint. And this is what you were going to be running today. So if you're working through the setup instructions or have worked through the setup instructions, it's for setting up the Solo topology. And at the end of the day, I'm going to reimburse you for your costs. So I know some people, the cost of coming to Strange Loop was right at the edge of their budget, and using the Solo topology today might have been a budgetary concern. So I am actually going to stand at the back of the class at the end of the day and reimburse everybody for their AWS bill that they incurred running the Solo topology. So this is what the Solo topology looks like. You are a developer working on your laptop, and it's almost like using S3 or anything that feels like a service in AWS. The only difference is, from feeling like a service, is there's this Bastion server in the mix. And the reason that this is there is that we want to be secure and locked down by default. So there's a lot of people who are trying to put databases on the internet. We do not want to put databases on the internet. So when you're running Datomic in your account, it's running inside of a VPC that nobody can get to, which is awesome until you want to kick the tires as a developer, and you find out you can't get to it. So the Bastion lets you poke open a hole just for you that's an SSH tunnel so that you can get onto the database. And then you have, once you wanted to go to production or something, you would have your client running inside the VPC with your compute resources, and all of these things delegate out to the storage resources that we'll show more later. When you do this, you get all of the things that you associate with running in the cloud. You get an integrated dashboard. Everything is automated through CloudFormation. How many people can read all the line items in the CloudFormation on that slide? Right? You'll never have to. So this is the automation that it takes to stitch together the different Amazon services, which are primitives for Datomic, into the construct that you see. This represents our research into Amazon best practices codified in a CloudFormation template. You press a button, and this runs through to completion. And you can go look at it. You're certainly welcome to. It's running in your account. You can go look at the template and look at how the pieces fit together. But you don't have to look at this at all. And I include this here just as a marker for these are all decisions that if you were going to build a thing on the cloud raw, you would have to make decisions for yourself about. So these are decisions that have been made. It includes integrated logging. So you can go and look at logs in CloudWatch Logs. It includes integrated tagging. So AWS has the ability to tag resources. This doesn't seem like an issue at all when you first get started and you're running your one thing. And then your account takes off and gets used for more and more things. And then suddenly you're running 100 things. And you're like, which resources are actually associated with this job? So everything is tagged so you can find all the Datomic things. And integrated security. When you talk to Amazon over the internet, they secure things using your, what do they call it? AWS secret key and credentials. And they use that to do a signature called the AWS HMAC version 4. Datomic Cloud uses that same signature algorithm. So your communications, your authentication is done using your regular AWS mechanisms. It uses what's called IAM, Identity and Access Management, I believe. All of your data is encrypted at rest. Again, this is where the cloud shines, right? Amazon Web Services has automation for all this stuff. So your data is encrypted at rest using keys that are managed by the Amazon Key Management Service. You're isolated in a VPC, and then you can optionally come in through the Bastion, and permissions are controlled via IAM. I want my storage to be low latency, low cost, ACID, and reliable. Can I have all those things at the same time? Not really. But it turns out, and this is going to happen again and again and again, I'm just going to ask this question right now, and I'm going to teach you the answer. And then later in the day, I'm going to ask the question again, and I want you to be able to shout the answer back. What is the magic sauce that makes it all possible? That's the question. And the answer is immutability. So we'll try it now. What is the magic sauce that makes it all possible? Immutability. One more time. What is the magic sauce that makes it all possible? Immutability. So it turns out that once things are immutable, they can't change, right? Then you're free to copy them around to other places. And so we do, relentlessly. So when you put data in the system, it gets copied onto your local hard drive, which is an SSD. That gives you low latency, but it doesn't give you very good characteristics for the other things, right? But we also put things in DynamoDB. When we put things in DynamoDB, that gives you the ACID properties. Dynamo's capable of delivering that. But we also store things in S3. What does that give you? How many nines of reliability do they advertise? Has anyone looked? 11. AWS advertises 11 nines of that you can get your stuff back. Not availability, but that you can get it back. They have a pretty high advertisement for availability as well. And then we also store things on EFS. And this relentless copying doesn't require any coordination. Because when things can't be changed, this is an important point, when you can't change things, you don't have to coordinate. What's the magic sauce that makes it all possible? Immutability. Right? And this is a very cool aspect of Datomic that's underappreciated even by people that are using it regularly. Because we're running on top of these storages, they can auto-scale for us. You don't really see S3 or EFS scaling. You don't really look at that very much. I guess you can look at AFS. S3, you don't see scaling for you. You just use S3 and forget about it. But with Dynamo, you can actually watch it happen. So this is watching the lines are flat, and then we do a batch job that has a bunch of writes in it, and Dynamo scales up to absorb the writes. And then when the batch job finishes, Dynamo scales back down. This matters for Dynamo in a way that it doesn't matter for S3, because in Dynamo, what do you pay for? In Dynamo, you pay for provisioning. Right? And that's important to the story here. We want that because we want the ACID properties. But Dynamo, relative to these other things, is expensive because it has this superpower. But we can turn this superpower exactly as high as possible as we need to get what we want. So that's what you have when you're running the solo topology, the thing we're going to be running today. Later, maybe you want to do more. So the bigger version of Datomic Cloud is what's called the production topology. The production topology is always clustered. So instead of having one machine, you have many, no single point of failure. There's an application load balancer, so you have high availability. If one of the machines becomes sick, traffic can be redirected to the others. You're inside of an auto-scaling group, so when you want to, you can start thinking about elastic auto-scaling, and you can add query groups, which we'll say more about in a minute, that are specific to a task. So here's what the production topology looks like. Again, you're some client, potentially outside of the system, moving along, using the SOCKS proxy to connect through to the Bastion. But now the thing that you go through is a load balancer, and that load balancer directs you not to a single node, but to a group of nodes in what's called the primary group. You can then, and this is actually a fairly big system shown here, you can then run separate groups for separate jobs. So if you have and we've seen this a million times. So Cognitect has a consulting arm, and people will come to us and say, we have successfully built a web-based startup, and now we have some batch jobs that we want to do against that same data that's coming in from our users. And what are the requirements people have for those batch jobs? It's always the same, right? We want those batch jobs to not impede the flow of the regular system. I don't want to say, sorry users, we're running our batch job right now, we have a scheduled maintenance window. And we want to have those batch jobs run against the very latest version of the data. And a lot of times what people end up doing is compromising, and they say, you know what? We cannot put this load on our system, so we're going to copy the data to another system, and then we're going to send the load there. And sometimes they say, you know what, that other system, because of the kinds of queries we want to run, we're going to use a totally different query language, which means a different data model, which means an ETL job. Once you have that all set up, you've doubled your operational complexity, right? You and your operations people have to know how to run two different things. You have to know how to use two different things. And of course, you're always lagging. Right? And I've worked at a ton of places where they're like, yeah, we can answer these kinds of questions in 2 minutes, and these kinds of questions take a week, because we run the big weekly backup, every Sunday night into the other system. With this approach, you can say, you know what? We've discovered we have some analytics queries that we want to run, and we do not want them to get in the way of everyday use, so we'll just start up another scaling group. And notice that we are starting another scaling group. We're not just scaling within one group, because we have two different kinds of work. So it's not just that we want scaling, it's we want those things not to be competing with each other at all, and to be able to make independent decisions about those things. With the production system, you get a much more elaborate dashboard, and there's a lot of things that get bigger, like this. And then you get the ability to do these query groups that we were just looking at. So query groups let you have compute resources dedicated to jobs. These can come and go on the fly. Another thing that people do is they say, you know what, we can't serve reads fast enough off of one machine, so we're going to shard. And we're going to put all the A's through E's over here, and all the F's through M's over here, and all the N's through Q's over there, and then all the R's through, I can't remember the alphabet, whatever the end of the alphabet is. But we're going to shard our data, and we're going to put the data in different places in order to serve reads. This is terrible, right? Because it requires you to make an upfront decision about where you're going to put data, and then it introduces a piece of structure that people have to step through to get to the data. Now you're not saying, give me the Twitter ID of this individual. You're saying, go to the E through M place to get the Twitter ID of this. And so it invades your programming model. So sharding is terrible. Now, remember, we're not talking about building a right-scale system here. So on the right-scale systems, it totally makes sense to shard. I get it. But when you need to read scale, there's no need to shard, right? What's the magic sauce that makes it all possible? Immutability. If we need to read scale, we can just copy everything over to another place with a bunch more compute resources, not a problem. And that's not hard to do. And so we can make these data decisions without deciding up front. And here's an example of using query groups for operational stages. So this is another place where you might use them. So here we have a developer who's working against a query group that has a tiny instance, right? Because we short our developers all the time. We never let them play on the big instances because we're very budget conscious. So they get to work against a small instance. Then we have CI is running a small instance. Staging is running a small instance for internal stakeholders to poke around. And then when we go to production, we have an auto-scaling group for our actual server where the instances are bigger, and we've set it to be able to scale from 2 up to 6 instances. So this is another way. So now we're, instead of dividing things up by function, web server versus analytics, we're dividing things up by stage in the development process. So you can say these people will go to this resource, these people can go to that resources, all within the same system. Now, we did a thing. We made this thing, and it was great. And so Datomic has been around for 6 or 7 years now, and Cloud is new in the last year. And as soon as we shipped Cloud, we realized that we had shifted a problem from one spot to another spot in the system, because we had made this thing that gives you a database that deals with a lot of AWS. It deals with auto-scaling. It deals with encryption. It deals with authentication and access control. It deals with storage. It deals with tying all the things together. All these different things that you have to know to do AWS. And it's like, ta-da, here's a database. Now, go write your application. Womp, womp. So now you have to go write your application. Well, where are you going to put it? Oh, it needs to run in the cloud. It needs to run on AWS with my database. Okay, well, now I need to secure it. Oh, right. I have to figure out and think through IAM. I have to think through encryption at rest and KMS keys and who knows what else. Oh, and I need to autoscale it. Oh, I guess I got to learn about autoscaling and how to configure that. Oh, and so it's like, wow, everything that you want to do about an application turns out to be something we already did for the database, which, of course, is an application. Right? So we built all this infrastructure to let you run your database, and as soon as you start to build your app, the first thing you're going to say is, wow, I wish I had all that infrastructure for my app. And so we did that. So Datomic Ions let you write Clojure code and install it into Datomic Cloud, where you get access to and benefit of all these resources. And the development workflow for this is you sit at a Clojure REPL and you interactively develop a function using the client API to connect, and then when you're happy, you install that function and you run it from the cloud. And this uses AWS Code Deploy to install the code. So this is a rolling, no downtime code deploy. So you could have a system with 20 machines that you're happy with. You know, you're ready to go to production, you press a button, and 15 minutes later, it rolls them one at a time, a minute per machine, whatever, making sure that each machine is healthy. You're now running your new code in the cloud. How do you get to that code? Remember, everything's inside of a VPC. So the thing that we added with Ions is we answered the question, okay, we told you how to get to it for development with the Bastion. Now we need to tell you how to get to it for production. And so the other thing that Ions will do is they will automatically create lambdas that act as entry points. So you can say, let's say you have 5 entry points to your application. 2 of them represent 2 different web services, and 3 of them represent event handlers for other things that are happening in AWS. You register those 5 things as exports, if you will, from Datomic Cloud. And Ion Deploy will automatically create a Lambda that delegates to that. So you can access everything through AWS Lambda. But unlike with Lambdas, once you're running inside of Datomic Cloud, you now have in-memory access to your database. So this was a big component of Datomic prior to cloud, which was what was called the peer model. And the peer model was you write a library, and your library is inside the database, which means when you access the database, you're accessing the database at memory speeds. You don't have to make RPC calls. It also means that you don't have what people call the N+1 problem when they're talking to a database, where they ask a question, and then they need to ask a question about the N sub-details, and they ask those questions one at a time. Now, you don't have those kinds of problems because you're running in memory with the database. Ions bring back the benefit of the peer model in cloud, because now you're installing your code and it's running inside the database. Now, does this mean that your application no longer has layers? Am I saying, hey, 1980 called and we want to go back and run all of our code in one layer? No, not necessarily, right? Remember query groups. You can say, this one does this job, this one does this job, this one does that job, this one delegates to that one. So if you want to introduce stratification and layers, you still can. You can just put all those layers inside Datomic Cloud. And of course, you want to get started with that web app. The API gateway, which is Amazon's technology for handling being the front door of the web, can delegate to Lambdas, or in a future version, can delegate directly into the load balancer. So this gives you the ability to say, I'm going to deliver my entire web application on Datomic. So that's what we're here to do today. Right? We want to have the information model of Datomic. We want to have the ACID properties with our data and know that we can get data into the system. We want to have logic and know that we can get the data out. We want to be able to deal with real-world information which does not show up in rectangular tables. Right? It shows up in arbitrary shapes. We do not want to forget the past, and we want to know how things got there. And we want to be able to get started easily at low cost, so we don't have to go get permission from somebody to run it. And this is what we've set out to do with Datomic. So that's what we're going to do. Here's the agenda for the day. We're going to go through sort of 5 different logical steps in explaining Datomic. The first one is, what is the information model of Datomic? So understanding how Datomic delivers the flexibility and capability to deal with hierarchy and modeling of time and all those things, which is called a universal schema. The second thing is how Datomic does transactions, which is ACID. So hopefully this is pretty familiar to people if you've had background with SQL databases. If not, we'll cover it quickly. Then looking at the query model, Datomic has a logic-based query model, Datalog. It also has a selection-based model for pulling back information called pull. Then we'll look at the programming model, which is IONS. And then finally, look at what it feels like to operate Datomic. So, in just a minute, we're going to take a break and make sure that we can get everybody set up to run Datomic Cloud. So the first lab is going to be getting the tools running and getting connected to Datomic. It's perfectly fine to work ahead if you've already done this. This is exactly overlapping with the instructions I sent out by email, but this is, we're going to take a half an hour break. We will pick up again at 10:30, at which time we're going to have made sure that everybody has gotten Datomic Cloud set up. Any questions before we break? It's okay to ask questions. Yes? How do we know if we are set up? So as you go through those steps, the last step, connecting, each step has feedback that will say, if this happens, you did it. So you will have seen a transaction happen against Datomic and pulled data back by the end of it. Any other questions? All right, let's break and work on the lab, and I will check back in with you at 10:30.